Okay, now another concept from computational attributes, the memory efficiency. Well, you know what memory is. Memory is where we keep our data. In a desktop computer, it's the hard disk. In an embedded system, it's the flash memory, flash card. If you have taken my embedded systems course in your undergraduate level, I explain all different memory devices. So it's a very important concept because memory efficiency in embedded systems covers also architectural design concepts as well. Because memory is something that you must access. Okay, I mean you have a CPU or a GPU or an FPGA and you're implementing AlexNet. Well, you have megabytes of knowledge there, weights all over there. Although they could be floating point or they could be integer. If they're integer, they require less space. But in the end, you have hundreds of thousands of weights, and you have to access them. Actually, memory efficiency is about accessing that excessive amount of data. Very briefly, when implementing deep convolutional neural networks, our processing units, CPU, GPU, FPGA, it needs to extremely fast. It needs an extremely fast access to incredible amounts of data, and sometimes it needs to move data from one memory to another, depending on the architecture. A good example is the GPU memory, because when you're dealing with GPUs, you have a CPU which is running the main code, and the GPU which is doing the hard work, like the convolution operations. Okay, so you're going to just do a convolution operation in one of the cores of the GPU. You send a simple part of the weights and the image to that GPU memory, and some other part to another GPU core. So it's not only accessing, but it's about moving between different architectures as well. And this becomes an architectural issue. So memory efficiency is an architectural issue, and it directly affects your speed, your computational power. Okay, we've done co-design for memory efficiency, you remember? Because in class we have done an AlexNet quantization live code. We have it on the live code sessions as well. Where weights were it's quantized into 8-bit precision, and since they were originally single-bit precision, which is floating bit precision, which is 32 bits, when you make them 8 bits, you get 4 times memory efficiency, right? That was a co-design. So using co-design, you can do architectural algorithmic advances. It can help the memory efficiency. But there is this total hardware dimension of memory efficiency. Because FPGAs access memory in a different manner, GPUs access them in a different manner, and TPUs access them in a different manner. There are different levels of cache memories. They are designed for cache memories. Cache memory is an intermediate level of memory between your processor and the main memory space, so that fast operations, access operations can take place. They are called cache. And for GPUs and TPUs, since you are providing your weights or data to thousands of cores, you need various levels of cache hierarchy. And actually GPU design and TPU design is architecturally about designing those cache hierarchies, guys. We are going to give them an introduction in the following slide, so don't worry about it. So I found a very nice slide, a paper. Let me show you that paper, guys. It's a very nice paper. I'm going to visit this paper in the following slides as well. It's multi-level granularity parallelism synthesis for FPGAs. It's about FPGAs, but it's about accessing data on FPGAs, and it makes very nice comparisons, guys. You can just download the full text from here. It's here, so I just, as you can see, very nice studies. It's about the implementation of deep learning systems for FPGAs and their capability of parallelism, because in the following slides we'll see that the biggest advantage of GPUs are their parallelism. So how can we make parallelism on FPGAs? This paper discusses. We are going to come back to this paper again. So there's a total hardware dimension. So is FPGA or GPU, is it better? you need to compare for specific applications like these guys do. Okay, we're going to come back to it, don't worry. So it's a nice comparison about latency, because we define the memory access times as latency. How much latency does it create to just access it? Okay, we'll talk about them later. And I'm just going to talk about them later in the GPU FPGA parts, where I'm going to define what a kernel is. Okay, and there's a final, maybe last for our slides, but not the least, dimension which I called stability. Because if you have ever worked with an embedded system, you'll remember that it's a total pain in the ass. I mean, you're trying to just upload something, you're debugging it, it doesn't work. You change something, it doesn't work. You think that it's working, then after a while it doesn't work again. So working with embedded systems are difficult because they have these stability issues. And sometimes, most of the time, the reason that it's not working is some small mistake you do, but sometimes they don't behave stable. Which is running on an embedded system is not running on another instance of the same embedded system. So it's called stability, and it's mostly overlooked, but it becomes a real problem in real-world applications. I've seen it become a real problem in real-world applications. And what are the issues of stability? For example, non-responsiveness, system hangs, abnormal restarts. They happen because these embedded systems, CPUs, FPGA, GPUs, they are very, very complex systems. And they do these undesired things like non-responsiveness, system hangs. And it is very difficult to debug why they do it. Sometimes, for a generation of embedded systems, these happen. So they are very low-level systems, and as they get more advanced, stability becomes a factual concern. So, for example, stability in FPGA systems is a very, very, very important concern. I mean, there's a nice paper from Altera. Altera is an FPGA producer. They are talking about the concept of stability for FPGA systems. Because in FPGA there's something called the streaming, and zeros and ones change very fast. And while they are changing, they are not changing properly. And this creates an instability. And this creates unprecedented errors. You cannot foresee those errors, but they happen. So metastability, they call it, can cause system failure in digital devices, mostly in FPGAs, because FPGAs are timed streaming bits running on buses. When a signal is transferred between circuitry and an unrelated asynchronous clock domains, this happens as they define it. Asynchronous clock domain is you are doing an operation, then you are doing another operation with the same input somewhere. Imagine a units architecture, and you have to just get them together in another block, like a concatenation block. Well, you need to get their timings correctly. Well, you cannot, and this asynchronous domains, you cannot just make their timing correctly because there's this metastability issue. So stability is also an issue you should consider. If you want your system to work properly always, then you wouldn't want to work with an unstable system. Okay. It was nice up to now. Now I'm going to continue with the hardware platforms, because for the last few slides I've been talking about CPUs, GPUs, TPUs, FPGAs, and what are they? What am I talking about? Okay, let's cover them now.